Okay, so now I can start with the new topic, and for the remaining like 15 or 20 minutes or something, I just want to make a brief introduction to the new chapter, which is the continuous time Fourier transform. Abbreviated as CT for the continuous time, FT for the Fourier transform, CT-FT. And trust me, you already know it. You already know the continuous time Fourier transform, so why do we dedicate a new chapter to that? And how come you already know it? I didn't mention about any Fourier transform or anything. Let's look at the previous page. Alright. Yeah. It's here. The top one is the continuous time Fourier transform formula. Without saying that it's the Fourier transform, but only by saying that we need to find the frequency response of an impulse response. From h of t, we formulate it like this to find h of j omega. That formula is the Fourier transform formula, okay? Without saying. And you may guess that the next chapter after this is the discrete time Fourier transform, and guess what? The discrete time Fourier transform is this one. Here. That is the formula for the discrete time Fourier transform already. So we know the formulas. So why did we open a new page for that? Okay, it's here. Why did we open a new page for this? The reason is that it's not only for the systems. It's not only for the impulse response to a frequency response. We know it. But it's also for the analysis of the signals themselves. So if we have x of t, then by Fourier transform, the signal will also have a Fourier transform, and it will be notated as x of j omega. Remember that this is for the continuous case. That's the notation. We use j omega to distinguish between the discrete and the continuous case. And the formula for this is x of j omega is equal to, just like the formula for h of j omega from h of t. Instead of h, I write x of t now, e to the minus j omega t dt. This is the Fourier transform formula. And this Fourier transform formula translates our signal from the axis of time to a completely different axis of frequency. Now our new representation is in terms of omega. So by looking at x of j omega, if you draw it on the omega axis, of course it's complex, so you may want to draw the magnitude of it or the angle of it, whatever. But suppose you plot it, what you see will be the harmonics again. If it has several, if it's a combination of harmonics or something like that. Or if there are not specific harmonics, the harmonics will look like peaks at certain frequencies. At omega 1 we have a peak, the others are small. And then at omega 2 we have another peak. So the time domain signal x of t is, you can say, it's a combination of two sinusoids at those frequencies. But suppose it's not like that, but it's at zero frequency range, it is high, and then it is small. What you say is that it's a low pass signal. It doesn't contain high frequencies, it's a low frequency containing signal. Or it may be a band pass signal, just like band pass systems or band pass filters. So you may want to analyze signals with respect to the frequencies, with respect to their frequencies as well. And those frequencies may carry information. The whole idea of compression, let me say, is many of the technology that you use in your daily life uses this kind of a transformation, and you're not even aware of it. It's like the compression of videos and images, or the compression of audio, music. In music you have the famous MP3, right? Extension, .mp3. That is an MPEG audio layer 3, abbreviated to MP3. It's an audio standard for MPEG video, actually, and it uses Fourier transform, sort of, because it captures different frequency bands of the music and assigns different number of bits to each frequency depending on the significance of that frequency band. If the signal has a lot of energy in that frequency band, it analyzes, then it assigns a lot of bits to there, and for the places with low energy, it doesn't assign many bits. That's how MP3 works. So MP3 doesn't work well for signals or for audio signals which are full band, both low frequency and medium frequency and high frequency. If everything is in the music, then MP3 fails, because some of the bits are assigned to here, some of the bits are assigned to there. It should better be mostly bass or mostly treble or mostly medium range, so that MP3 performs nice in compression. In JPEG, the famous, where most of the groups have taken it, it is a variation of a Fourier transform, which is called the discrete cosine transform. I'm sure you have already found the DCT term in your projects. The discrete cosine transform is nothing but a real version. This will be a complex transform. A discrete cosine transform is a real transform. It makes x of j omega not a complex number, but a real number. But it is a Fourier transform. Okay. So we are using them for compression. We are using them for analysis. We are using them for communication of the mobile devices and things like that. So it's everywhere in our daily life. The technology depends on formulas. It's not only just programming or implementation on a circuit or anything. What is the idea that you implement on a circuit? Is this mathematics? So this is very critical. I believe that normally it must be taught to all engineering students, not only electrical engineering. But they sometimes don't do that. So I feel pity about them. You are lucky people who are aware of this spectrum transformation, the frequency transformation, which is also known as the Fourier transform. Okay, that's a very valuable mathematical tool that we need. The inverse technique is something that we haven't seen, but it comes from this fact. This is somehow related to, I'm not going to show it, I'm just indicating it. And by the way, in the book by Oppenheim, this derivation that I didn't indicate exists. So it may be a good idea to look at those illustrations. This is somehow similar to finding the Fourier series coefficients from the signal, the signal here. But these Fourier series coefficients are only valid if x of t is periodic. Here, for the general class of Fourier transform, it doesn't have to be periodic. It can be just any signal. It may start at some point and at some other point, not necessarily periodic. Any kind of signal will have a Fourier series coefficient, a Fourier transform. From here, do you remember the inversion? The way to obtain x of t from AK, do you remember that? By the way, there must be a 1 over capital T or something like that, but it's just a scale. X of t in terms of AK was summation, what's going on? Okay, summation k from minus infinity to infinity, AK, sorry, there must be a minus here, AK times e to the j k omega 0 t. This was the representation of the signal from the Fourier series coefficients. Now the book makes a limiting case where the samples are very much side by side to each other, so that they are touching. So it's not like an AK on the k-axis, but it is something in terms of omega, something in terms of the frequency on the frequency axis, because AK is also plotted on the frequency axis. You remember that? After 2 pi, they repeat themselves for the discrete case, for example. So this AK has a relation to x of j omega here and here. And this summation formula is reduced to a limiting case to produce something that is similar to, or that is precisely the same as the inverse Fourier transform. And that inverse Fourier transform formula that we have is x of t. Let's be rigorous about this, because I don't want to change the definitions with respect to books. It has a few definitions, unfortunately. X of t is one, with a 1 over 2 pi scale from minus infinity to infinity, x of j omega e to the j omega t d omega. So that summation at the top has it's like the Riemann sum approximation of the below integral, because we know that the integral can be represented as a summation of very small slices. That top is those small slices, and the bottom one corresponds to the integral itself. And notice the similarity here. It is ak times e to the jk omega 0 t. But k omega 0 here is omega. Omega is k times omega 0. That is the frequency, which appears here, e to the j omega times t. Not k omega 0. That corresponds to the true frequency. And it's not ak with k corresponding to a frequency. It is x of j omega, and it's not the summation, but it's an integral. So if you closely inspect the two, you will see the similarity, and in the book there is a derivation from the top to the bottom to find the inverse Fourier transform formula. For you, okay, I'm advising you this for the curiosity. Okay, you may just be interested in that. But what I expect eventually are these two formulas, the knowledge of these two formulas, the Fourier transform, the transformation of xt to xj omega, and the inverse Fourier transform, which is from x of j omega back to x of t. And I am going to write them all together again and put them in a box. X of j omega is equal to integral from minus infinity to infinity xt e to the minus j omega t dt, of course, because t must be gone, so that the output is in terms of omega. And x of t is equal to 1 over 2 pi from minus infinity to infinity x of omega e to the j omega t d omega this time. So these two formulas will form the inverse and the forward Fourier transform. The top is the forward Fourier transform, the bottom is the inverse Fourier transform. And we are going to use it to inspect signals in several aspects. And fortunately, the Fourier transform itself is a tad easier to understand and a tad easier to apply in examples. It's not as difficult as the Fourier series. That's how I think. For instance, it's the only example that we will see today. After this, we will finish. Let's take a look at this non-periodic signal. It is, of course, non-periodic because it starts at some point. And it's not an oscillation, but it's a real exponential, e to the minus at. In order to, by the way, of course, if you want to have the Fourier transform definition, the signal itself must be stable or a convergent signal. If it's not stable, if it diverges, then if it's not a convergent signal, then you cannot talk about the Fourier transform. So for that convergence, we need to have a greater than 0, so that e to the minus at will be a decaying exponential. Nice. So what's the Fourier transform of that? Just apply the formula. You don't have to be very skeptical about applying this formula. It's easier, as I said. Just apply and you will find the result. X of t e to the minus j omega t dt is the formula, which makes the summation to start from, the integration to start from 0 to infinity, because there is a u of t inside xt, and that makes all values x of t to be 0 before 0. And after 0, the values are e to the minus at. You don't have to put u of t, it is all ones in this range, and e to the minus j omega t dt. Let's proceed. Let's put into a common parenthesis e to the minus a plus j omega t dt. Right? We have combined the exponents. And the integral of an exponential is something that you can remember. One of the few things that you can remember from calculus. It's easy. That is the exponent in 1 over, but it's negative, so let's put a minus sign here. Minus 1 over a plus j omega e to the minus a plus j omega times t, integrated from 0 to infinity. Okay, do you remember this? It's a simple exponential integral. As I said, the Fourier transform requires a non-divergent, a convergent signal, because we need to evaluate this integral or this magnitude at t is equal to infinity. And at t is equal to infinity, this exponential must go down to 0, and it happens only if a is greater than 0. The complex part, the imaginary part, causes an oscillation. It doesn't contribute any divergence or any convergence. That imaginary exponential is just an oscillation. This e to the minus at thing is the damping or an increasing factor. And if a is positive, it's a damping factor, which makes at infinity this thing to be equal to 0. E to the minus infinity it makes. And at 0, at t is equal to 0, e to the 0 is 1. And we must subtract that. Subtract the value at infinity, subtract from the value at infinity the value at 0. So the subtract a negative thing will make a positive thing, and the answer is 1 over a plus j omega, and that is x of j omega. And it's a very nice, simple, compact Fourier transform. 1 over a plus j omega. Is this a low-pass signal? Is it a high-pass signal? What would you say? The low-pass, high-pass things are evaluated with respect to the magnitude of x of j omega and the angle of x of j omega. The angle doesn't represent anything. It doesn't mean low-pass or high-pass, but let's take a look at the magnitude of this thing. It's a complex number, and it has a magnitude and an angle. So the representation is as follows. When you combine them, it will be x of j omega magnitude times e to the j angle of x of j omega. So this is the complex number representation. So what is x of j omega in magnitude? What was it? It was 1 over a plus j omega. So we must multiply it with the conjugate and then normalize it. Well, what you will obtain is this. This is the magnitude. And by the way, the angle, let me write it here, but I'm not going to be interested in that. It is the arctangent of the, since it's in the denominator, it's the minus negative arctangent of the imaginary part divided by the real part. The imaginary part is omega and the real part is a. it is a plus j omega in the denominator. So the angle is arctangent omega over a. And if the expression is in the denominator, it makes a minus arctangent omega over a. That is something mathematical. This one is more important to us now, the magnitude. By looking at this magnitude, what do you say? Is it low pass, high pass, or whatever? Would you give a name to this? Where does it have the peak? When does it achieve its maximum value? At omega is equal to 0, right? Then it will be 1 over a. Somewhere here it is 1 over a. And then as omega increases, this magnitude decreases. Like this. As a function of omega. So, what sort of an attitude is this? It is somehow low pass. Because in lower frequencies it has higher magnitudes, higher energy. And at higher frequencies, towards the tails of larger omega, it has lower energy. And it's reducing down to 0 as omega goes to infinity. So you can somehow say that it's low pass looking thing. It's not a very nice exact low pass or anything, but it's a low pass signal. You can say. Okay, we will see other examples. We will continue with this topic, and it's a core topic. We have to be interested in these things.